because I don't know the net quality.
Yeah. Started.
So, welcome everybody to our webinar today. I'm pleased to introduce Dr. Jack Haddad today. He'll present today for us about his latest research. Dr. Haddad is an associate professor of transportation engineering at Technion-Israel Institute of Technology. He has done his all degrees at Technion, and he has been as a postdoc at EPFL for 4 years, and he's currently a visiting professor at ETH Zurich. His main research interests include autonomous vehicles, traffic flow modeling and control, large-scale complex networks, and advanced transportation systems management. So, Jack, the floor is all yours. Thank you.
Thank you very much. Thank you for giving me this opportunity to present you my recent work related to air mobility. The title of this talk is Modeling or Traffic Flow Modeling and Feedback Control for Future Low Altitude Air City Transport and MFD Approach. This work is under review in TRC with co-authors from my group, Mirkin and Asif. Okay. So first of all, I will explain the motivation and I will describe several issues related to the LAAT system. Then I will define the problem and derive an MFD. And then a new system model under anomalies and new control design will be produced. And finally, I will show some simulation results and finish the presentation with this. So low altitude passenger and delivery aircraft, are being developed as a new mode of urban transport. There are many companies involved in developing such vehicles, like Airbus and Volocopter in Europe, Boeing, Uber, Tesla in the United States. So the penetration of these low altitude passenger and delivery aircraft into the airspace cannot be prevented in the future, in the near future. And we estimate something about 100,000 passenger drones that could be in service worldwide in 2050, and more, expected more like millions of regular delivery, let's say regular delivery drones in the airspace city in the future. So what will happen that this will give rise to new urban air transport system, which we call it LAAT, low altitude air transport, LAAT systems. And similar to the road transport systems, increasing the numbers of the passengers and delivery aircraft will cause congestion. And once it causes congestion, will also cause or will raise new air traffic control challenges. Therefore, we think that we must investigate first the collective behavior of the LAAT aircraft in cities and the ways of controlling the LAAT systems. We believe that the MFD can facilitate, can help in the modeling and control of large-scale LAAT. So let's move to the LAAT issues that we need to handle them. So first, the current air transportation management schemes that are existing are limited, and they are limited to conventional airplane operations. They cannot be used to LAAT systems. They are based on centralized control structures, which means that we have like a human operator or controllers that responsible to ensure the air traffic to move safely and efficiently without any collision. Such control or management scheme implies rigid individual trajectory-based operations with fixed routes, pre-planned or approved aircraft schedules, and while ensuring conflict detection and resolution in the air. Regarding the operation of the future system, instead of in comparison with conventional airplanes, the operation of the future LAAT system is expected to be more flexible. For example, such system will allow on-demand point-to-point urban travel or delivery with a higher total number of daily short trips and under a more complex urban environment with energy consumption constraints, in addition to noise and weather consideration that should be taken. The LAAT aircraft also expected to be operated in under congested traffic conditions. This happened because given the large number of passenger and delivery aircraft, and also because they will be traveling in a very limited allow capacity. So in addition, we have a very unique dynamic property for the future aircraft, which is the hovering. So in this case, this is one of the key difference between drones and conventional aircraft. In congested, when we have congested regions, the hovering dynamics will introduce new interaction effects between the aircraft, like a platoon of drones waiting to enter a parking and waiting to enter to parking or any other building. So we need also to control such buildings. Regarding the aspect of control of future LAAT systems. So LAAT systems is a typical example of network control systems, and such operations will be carried out combining the new physical and network facilities. There will be strong interdependencies between various infrastructure. We will use communication technologies. All these will increase the system vulnerability for uncertainties, failures, and cyber attacks. So these issues should be focused on. So my point here is that large LAAT network should be robust to various anomalies in technical devices or network communication. So this is a very crucial point, because first we will increase the safety, and more important is to increase the community trust or the acceptance of such systems in the future. Okay. Given all these operation differences between the conventional and the LAAT aircraft, future aircraft cannot be managed by the current aircraft management schemes, because they are not dedicated to this task. If we utilize such a scheme, this will decrease the traffic performance of the future LAAT system. Therefore, and inspired from the urban road networks, we suggested to address the future air congestion problem based on a new operational concept. So instead of looking at individual aircraft, flows of aircraft traffic should be controlled. Okay, so the solution approach, and this is the main important slide in this presentation, is to develop traffic flow model and feedback control theory for LAAT systems. And we do this in 3 steps. First, we need to establish the concept of MFD. which is now widely used for ground urban traffic modeling. I mean, in the last decade, there was a lot of contributions for urban traffic network using MFDs. Last week in this TFT webinar, we also have a work that was related to MFD. And then we need to develop, once we have this MFD relation, we need to develop aggregate flow model with boundary control. We call it boundary control instead of perimeter control in urban road network. So boundary control because it will be plane, it will be two-dimensional borders in the space. So we need to introduce a new flow model for large-scale multi-layer air transport system. Once we have the modeling on hand, in hand, we need to develop a effective design approach for this boundary adaptive feedback control, which would be robust for anomalies in technical devices and network communication itself. Okay, so let's set up the problem. So first, we did the literature review, and we conduct a very large, deep literature review on this topic, and we conclude two things. First, that urban traffic flow models for LAAT system have not been fully explored. And the second point, that feedback control strategies considering LAAT system have never been introduced. Now, what we saw in the literature that there are several, or there are very limited works in the literature that introduce only elementary, let's say, elementary traffic-oriented models for microscopic at the level of aircraft or macroscopic at the level of a link related to LAAT systems. So here we show several of these. We focus on the last one, XU and DO. We take this microscopic model that has been presented in this work, just in order to model the microscopic behavior in order to construct them. So I will not describe the whole model here, but the main flow characteristic of this model are summarized in these three items. And actually, this model is present or consider an aircraft as a double integrator dynamic with some interactions. So in full description can be found in this. But the idea is simple. The idea that there is a safety condition and there is a clear distance defined in advance should be kept between aircraft at all times in order to keep the safety condition. So there is a look ahead time, and during this look ahead time is used to check if there is an aircraft which might or potentially violate the clear distance. And with communication, if this is really happened, each aircraft reports its future trajectory to every aircraft. And if there is, so there is two options. If there is no violation detected during the look ahead time, then the aircraft can freely accelerate to the maximum velocity towards their destination. But if there is one or more future violations are detected, then they should do a maneuver and should do new routing, to plan a new routing, where we need to minimize the deviation for each aircraft from its own initial trajectory. This is something that can be calculated in simple nonlinear integer programming. And this is what you see here in the figure. We shows microscopic results for 4 aircraft trajectories traveling from east to west, from west to east, north-south, south to north. And you can see that the 4 aircraft detect possible conflicts and relations, and therefore you see these changes and deviation from their original objective. And here we present one of the case studies that we investigated in order to extract an MFD shape for LAAT system. So this includes a squared area where each aircraft starts from one age and ends from a different age. They start from O, if you can see it, and they end up with the point X. I want to show you the simulation. I hope that it will work. So let's see, share screen. Okay, so this is, I hope that you see the simulation. If otherwise, let me know. Raf, you can see it? Okay, so what you can see here, we see so we see the space. So figure 1 and figure 2, they have same demand, but less size, okay? And then from 2 to 3, same size of area, but more demand. And as you can see, we have uncongested condition to moving to congested condition. As you can see in the congested condition, vehicles are hovering in the border. They cannot enter because it's very congested. Even recalculating the trajectory cannot help. They need to wait outside before they have some time to enter back to the frame and to enter back to the area and cross the area to their destination. Okay, so let's now see. We come back, hopefully. Okay. Can you see my PDF file?
Yes.
Okay, perfect. So, so once we show the simulation, now what we did, of course, we extract the MFD by doing some simulation for different level of flows, different profile. Then we calculate the generalized AD's definition, and we average those, and then we get this shape of MFD. This figure shows the MFD results, where it relates aircraft with completion float with the accumulation or number of airspace in the urban airspace. Okay, so we have, let's say, an MFD. Scattered, not scattered, this is another issue that we'll discuss later. And now we want to move forward because we need to set up the structural design of the airspace above the urban city. So only a few papers have recently proposed different airspace structure designs. So these papers, all of them, follow the concept that the airspace can be similarly structured as roads network. Okay, so there is a few works that consider the airspace structure at the micro level and the macro level, but we want to tackle the challenge at the network level. Therefore, we propose the following airspace structural design, where this can take into account special elements of aggregate network flow modeling and future control measures at the network level. So the airspace above the urban area is used for aircraft movement, and it is divided to multiple layers by altitude. And each layer, as you can see, is divided to virtual regions. So what we see here, we want to build a structure, we call it multi-layer structure, and it's controlled volume. And the airspace is decomposed again into L vertical layers. Each horizontal layer, similar to road infrastructure, is partitioned into virtual regions, okay? Where each virtual region has, as you can see, its own uncertain MFD. We define aircraft traffic flow H as the number of aircraft traveling per time in the horizontal direction, while V in the vertical direction. So this means that, as you can see here, the drones can travel vertically from one layer to another, or horizontally from one region to another at the same layer. So in order to control such flows, we also suggest what we call virtual distributing gateways. Gateways is something like signalized intersection, if you want. So they are distributed on the plane here. So we have 6 planes each region. So they are distributing over the plane like gates, and there are M numbers of such gateways on the horizontal regions and G on the vertical movement. Okay, so now we move to the system model, and we introduce a multi-layer urban LAAT system where the aircraft accumulation for the ICE region at the Lth layer is given here. So as you can see, it is partitioned or include 3 parts. The first part, aircraft with internal destination. The second part, aircraft with destination to region J horizontally. And as you can see, J are belonging to some set of regions that can be reachable directly from region I. And we have the same for vertical layers P, where P belongs to some set of regions that are directly reachable from region I in vertical directions. Okay, but as you can see in the equation, we have a third index. So the first two, so the first sum is summation over regions, and the second sum here, the M and the G, it is the index related to K and S. It is over the gateways, because in each plane we have different gateways. And the aircraft conservation equation would be given here. So the change in the number of aircraft in a region I of layer L is equal to the difference between inflow and outflow, where the first term here is actually the internal flow. In other words, is a flow that entering and finishing in the same region I. And the last term is actually the uncontrolled traffic aircraft demand. We consider it as a disturbance in the system, while the other terms here, the 4 terms, are the controlled input and output transfer flow between, again, interregional and interlayer gateways. Remember, H for horizontal flows and V is for vertical flows. And again, as you can see here, we have also 2 summations. Okay, so now we want to connect this with the control. So we take all these 4 elements and we write it in a vector way. So what you can see here, based on the actually on the MFD concept, we can distribute the flow. If you remember, in road networks according to the destination decomposition factor. So it means that the total flow is distributed between different regions according to the ratio of accumulation. But here, what we wanted, we have the MSDs, shell, G, and we have these weighting factors, which is very general factors, general nonlinear forms. It can be constant or time varying. We wanted to keep it very general. And here the U is boundary controls in each region, and it's related to specific to the gate, specific to some specific to the gateways. Okay, this also can be rewritten as a vector 1 with big U and big U R and UV. So finally, once we have this, we can write it or rewrite the nominal accumulation-based model, and this is a general nonlinear model operating in the nominal mode. What do you mean by nominal mode? Nominal mode is where we consider a nominal MFD without disturbance, without uncertainty in the MFD. Meanwhile. And the model includes, as we said, set of three equations according to the different destination. This is II, IJ, and RP, as I described earlier. But the nice thing is that we include here now, look at the U, now we have some operator D as a function of U, okay? And this D denotes a delay function. So there is a delay in the input, and this can be state dependent or delay time varying or constant. I open it, I keep it as general as it can be because this delay is a very powerful tool in order to use it to introduce more enhanced dynamic for the LAAT systems. So we can model different aspects, different issues in LAAT system by introducing delay. So there's also future or ongoing research how we define this, for example, delay as a function of the accumulation. There are several works that I did with the regular MFD with input delay that we want also to share these if it's in terms of physical meaning, if it holds for LAAT system. Another fundamental feature that we present here in the modeling is that we add delays, as you can see it here, in the states or in the other states, in the interconnections states. So we consider here a region I, but for N accumulation J and N accumulation P, for the other interconnection regions, we introduce some delays, and this is we'll describe in the next slide. It's related to, for example, some errors or failures or cyber attacks. Okay, so now we need to design the control, and in order to design the control, we need to simplify the nonlinear dynamics, but we don't really simplify it very much. We introduce what we call partially linearized uncertain model. So the first step, we modelize the model around an operating point and move all the states that we introduce to deviation form corresponding to xi, as you can see here. So again, we don't fully linearize the model. We just partially linearize it. So for region I, for example, this is the part, you can see here the two terms are linearized, but the rest, these results here are non-linear terms. We keep it as a non-linear terms. They are function of the adjacent xj adjacent regions. Okay. So we also need to consider uncertain model, and here we consider uncertain model because we will see later that all these matrices in blue are actually uncertain. And then what we have here input delays. We assume that they are known, okay, in the control. We also have state delays at the state here, tau, that we assume that they are bounded. They are bounded around Tmax, okay? So these delay we don't know in advance. They are uncertain, but they are bounded, and these bounds we don't know even in advance. So these are the two assumptions that we assume: bound on the delay, and also the derivative over time is less than. This will help us in the theory. Okay, so now regarding P, what you see in green, P. P brings together several items and nonlinear interconnections. The nonlinear interconnections, nonlinear offset introduced because we might choose a non-equilibrium operating point, and there is some high order terms when do the linearization. So all these will be integrated in this term P, and also most importantly, it will take also the potential unreliable communication between regions. For example, if we have denial of servers because of cyber attack and so on, so we add the delay in this term here, tau, as you can see. Okay, and this is uncertain dynamics that I mentioned before. So all these matrices are unknown elements, and the external also uncontrolled flow, for example, are unknown, but it is bounded, but the value is not. Okay, so how we design this? We follow what we call the model reference adaptive control approach to design the decentralized boundary controllers. There are many literature on MRAC, model reference adaptive control. I just explained here the main idea of the approach in simple words. So as you can see here, the scheme. So the scheme assumes that we have one control structure, which is depending on some parameter theta, but this theta, the gains can vary over time in order to adapt the situation or adapt the uncertainties in the parameters or other issues related to, for example, cyber attacks or other issues. So there is a block which we call it adaptive laws that we need to suggest in order to see how these gains change over time, right? And in order to do this, we get help what we call from reference model. So we have some reference model. We introduce some trajectory, some model that reduce some trajectories that we need to track it. So this will help us in order to derive the adaptive law such that the controller bring the state to the trajectory that we want. Okay, so the question, if we can use a control structure and adaptive law algorithms from the literature, and as far as I know, no, we need to develop our own control structure, and also we need to develop our own adaptive laws for the current problem. So when we use MRAC, model reference adaptive control, with non-constant input delays, especially when we talk about decentralized control structure, we need to introduce something new in the theory to handle it. Okay. So let's consider the decentralized controller, and what we do here, we consider the design in an event-driven frame. This is what we see here, event detector and the whole. So we focus on the case of sample and hold, sample and hold of the control signal. So the idea is that the control is not continuously implemented for the urban region, but it is transferred only at some certain instance t k, okay? And this instance, we call it some events, and these events occurs when, for example, the control variables deviate too much from their required or expected values. So to identify this deviation, an event detector here is included in the control loop. So the event detector monitors the control continuously and check it and compare it with a pre-specified logic rule that we suggest. And if if it is violated, then we will apply the control step. If it's so we will apply it only if the control is, if this threshold is violated, but otherwise the control action will be. And this is actually very important in terms of practical implementation in the future, because you don't need to continuously calculate and send orders for the aircraft. Probably in the future with many aircraft, you need to send some discrete decisions over time. But the key point here that using the event-driven paradigm or framework will help us in designing the algorithm, because the idea of the design is presenting here, and it's very simple. We have some difficulties, and some difficulties in the adaptive control when we have delays is to protect the planned state, giving the delay in the near future. But to overcome this difficulty, we can reformulate the model that we presented to an equivalent plant for design while extracting these delay terms. So what we do first, we introduce non-delay control inputs. Then we relocate the delay control inputs, these ones, as we relate it as a component into some service signals. These signals, auxiliary signals that we produce, and built with the help of the event detector rule that we presented. We can define different event detector rules. We define here this one, which is the difference between the continuous and the discrete one, and the discrete one with the delay should be less than, the norm should be less than some pre-specified value. So the idea is simple. So we start with the model that we presented, this model, and now we reformulate it as the bottom model. And as you can see, we will get rid of the delay in the input here, and by introducing some new auxiliary signals, as you can see here, from the event detector, and this new signal will be removed to the right-hand side here, and will be considered as a disturbance. Okay, so this is again the new model, and this is the observation. As I emphasized here, this will be treated as external measurable, and this is important because it's a measurable disturbance that can be measured. Similarly, how we can deal with plant disturbance. So the nice thing is that we pull the input delay out of the control flow. And we have what we call input delay free case of a control system. And for this, we have various procedure for control design. And now we can design the control. So the control objective is to design feedback tracking controllers that can only functioning with local online information, only according to some information from the specific region I. But the closed system should be stable, and the states of the system, state of the region of the accumulation, should track some reference model that we present here. So this reference model is described as a linear state dynamics, where for each movement or for each region I, there is a state vector, reference input, and some constant matrices. So this is a very general, it can be any model to produce any trajectory, but we also can produce constant trajectory. So for example, in typical MFD, when we do parameter control, we regulate around some specific points, so this can be constant. If you want to make tracking, so you just suggest some tracking formula, for example, to minimize noise. So you can introduce this as this model, plug in here, and we can, the idea is to track the output according to this reference. This is the parameter adaptive rules that we suggested. It's a function, the adaptation is a function of Z. Z is a function of omega. And you notice that omega is a feedback signal from the reference state of the reference that we have, the input of the reference that we have, and also E, which is the error. This is what we call the tracking error equation between the current state, the real state of the system, and the reference state according to the reference model. And actually, this error tracking equation or tracking error equation help us to prove stability, and this is found in the paper. So finally, the controller that we suggest, each boundary control for each region has two parts. This is the two parts presented here. And once you implement it, again, it's a function of omega, which is a feedback of the error, the reference state and input. And once we do it, we will get this theorem that if you, for the system given by the partially linearized model and the reference model that we suggest, the decentralized adaptive control that we suggest here with this structure and the adaptive rules, all the closed loop signals will be bounded and the tracking error will go to 0. So we reach the destination, we reach our goal. Okay, so let's make it short for the simulation. This is the simulation results. We have 2 layers, 3 regions, 2 MFDs in the lower layer, and 1 MFD in the higher level. And as you can see, we have a flow that can travel vertically, horizontally, internally, and so on, all options. And we suggest MFD for each region. We assume that each region, each virtual region has an MFD, and these figures show nominal scaled MFDs. And we also have some disturbance, but it's important to emphasize that the disturbance are assumed unknown for the controller. We don't know it in advance. And what we show in the results of the simulation, we show here simulation of the distributed adaptive boundary control for this two-layer system with the three regions. So what we see here, we see the error, we see the disturbance, we see the control from region 1 to region 2 and from region 1 to region 3. Probably this is the vertical one, that one is the horizontal one. So this is the first set of 4 figures, and this is another set for similar figures but with different threshold parameter values in the detector's rule. And as you can see, we see that the error goes to 0. We assume a simple case of constant accumulation to track something near the optimum. We have some delay, we have some disturbance again, some jump, but it is not known for the controller. But the controller, as you can see here and here, it is a piece, it's like stairs function. So we have the continuous one, the continuous value that it is calculated, and we have the stair ones, which is operated by an event trigger paradigm. This is the red one, what implemented to reality. This one is calculated in the back of the controller, how you say it. They calculate it all the time, but they don't implement it. They implement just the red one if you pass the threshold or violate the detector that we mentioned earlier. And this one you can see for different thresholds. For example, here we have one implementation, second step, two stairs, 2 times we send for the plant. And here, because the threshold, we change the threshold, we just send it once. And with this given rules and thresholds, we can see we can still succeed to bring the error to 0. So if we have some initial accumulation, we bring it to the reference and the error will go to 0. So we reach our goals. And this is the same for region 2. And this is for the same for region 3. And I will keep time for questions. So to summarize this, this paper actually constitutes only first, let's say, primary steps towards theory and practice for both aggregate flow modeling and adaptive feedback control for LAAT systems. We developed the model, we call it multi-region, multi-layer, multi-region aggregate model based on the MFD. And after this, we design a decentralized boundary control for each virtual region with an event-driven paradigm framework, which is also robust against different uncertainty with non-constant input values. And with this, I finish my presentation. Thank you, and I'm happy to answer any questions if you have.
Toda Rabba, Jake, thank you for your interesting presentation. So we are now open for questions. Please feel free to unmute yourself and ask your questions.
I would like to ask, so do we know anything about the shape of the MFD?
Can I see you? Can I see you? I prefer to see your face rather than to see.
Okay.
Yes.
Do we know anything about the shape of the MFD and how it compares to traffic, regular traffic?
Look, the shape of MFD is very interesting. I cannot say that I fully investigated the shapes of MFD. We just started. And
nobody's done this, right?
Sorry?
Nobody's done this.
No, there actually there are some works in 2018. I can see it in the paper. If it's interesting, I can tell you the reference, exact reference. But he didn't call it. They didn't call it MFD. They call it something like relation between throughput and inflow. okay? And they show this relation corresponding to different headways, minimum headways that you can accept. They didn't call it MFD, but it is there. And actually, MFD, I also saw, I heard some other researchers that they start to do some MFDs for air mobility. But this should be more investigated, seriously investigated. What I see here, I only see one scenario for which is extracted from one microscopic model, but it should be investigated more. The key point here is that we need to go, I need to go in different tracks. One, to investigate more MFD shapes. And the other one, once we have the MFD, I present here some framework to use this for modeling and for control, which is the main focus of this.
Now, the measurements in the figure are what type of measurements? Sorry if you said it.
Sorry?
In the figure, there's measurements?
Yes.
So what are the measurements?
Okay, so it's typically you calculate the number of aircraft inside and those waiting in the perimeter. So this is tricky because
but this is real data. It's not simulation, right?
What do you mean real data? I don't have real data for aircraft, no.
Oh, but when you say measurements, then you mean from the simulation.
Yeah, sorry. We need to
okay.
according to this model here. Sorry, we need to change the term. You're right. This is typically according to this model here,
I see.
and the simulation that you saw.
Very good.
There is actually, Jorge, there is no real data. One option is to do a lab that can test this.
What about regular aircraft?
I asked for funding for that, and it was denied. But it will be a nice idea that if you can take some aircraft in a lab environment and you do some MFD. I know that NASA do a lot of work, and they have 2 mega projects, 5 years and another 5 years, but they do microscopic modeling behavior, but not macroscopic modeling behavior. So they don't use the microscopic modeling that they develop in order to extract MFD. And one option is, once they finish developing it, maybe also can be used as a better description for the microscopic behavior than this model that I present. Or you introduce a better one. Because there is some issues that need to be tackled in microscopic models that introduced here. So there is, for example, it's not clear what is the spacing that you need to keep. It's not clear.
Yeah. So let me ask you this.
Yeah.
What about using the data for real aircrafts going from city to city as a proxy for what you're trying to model?
This is a very nice. We already did this in one of my papers with Kihan. So we have a paper in part B modeling an MFD shape for a relation for the number of the airplanes waiting in the airport and the landing and taking off flow.
Yeah, well, but that's different, right?
But this is different. But we have the data. We have the data. Nice.
Yeah, but you don't need waiting times at airports or anything. It's just the airplanes in the air, right? That's our infrastructure now. So I'm sure they have data, right, on that.
But even if you have a data, there is a big problem. Because there is a very important property, it's written here, the hovering. You don't have hovering for airplane. So what we
But they
saw
go in circles.
Yes, but still Circus is very, very large and he's still moving. So the
Jack,
velocity
all I'm saying is that you don't have data, but there's data that you could use now with some caveats, obviously, right?
Yeah, this is a nice idea.
So it might be worthwhile. All right, let's see if the audience is awake.
It's a morning in your place, right?
Yeah. I guess they're not. All right. Thank you, Jack, for this nice presentation, signaling the future of applications of MFD. Rafa, do you want to announce our next speaker and when is it going to be?
So we don't have any speakers for this year. We'll have announcements soon for 2021, considering the holidays.
All right.
Yeah, next week, Christmas.
So Jack, thank you for bringing us to the end of this year in the Traffic Flow webinar series. Hopefully next one will bring more exciting topics and look forward to seeing you all.
Thank you very much. Have happy holidays and see you soon.
All right. Happy holidays, everyone. Stay safe.
Bye.
Bye.